Welcome to week 2. When are we? Last week we talked about where we are in the universe. This week we are going to talk about when we are in the universe. We're going to discuss star formation and misinformation. That is my haha funny little joke there. All right, so do you have your students do any estimating to recall prior information? Maybe just to flush out information. You say something like, remember when you learned blank? What can you recall about that? Well, this week we're going to learn about when we are. Last week, again, we talked about where. And when we ask students to recall what they've learned, they may have conflated information into their memory, post event memories, making it hard to undo misinformation. And so, after we learn a little bit about when we are, so that we can learn some space science today, we're going to talk about different ways to look at misinformation. So, here's a list of events. If you were to spread them out onto a football field, so let's say I handed you a card with each number and you walked from goal line to goal line, setting them down, where would you place them? So here's the Prospect High School football field. Go Knights. Where would you place these events, 1 through 10? I shared this image with you on Schoology if you want to actually try and write it down. So you would put the Big Bang on the left there. You can see I've already got it labeled, and today is on the right at the other goal line. And I have my students do this to see just if they have any sense of where these events occurred on a timeline that looks like this. So if you want to try it on your own, go ahead and pause the video. Otherwise, let's go ahead and take a look. So starting with the Big Bang, we would walk to about the 2 or 3 yard line before we see the very first stars forming in our universe. And today we're actually going to talk about stars and the life cycle of stars. On the 5 yard line, galaxies would begin forming. And so all of that didn't happen immediately after the Big Bang. In fact, there was a huge period of darkness between number 1 and number 2 there after the initial Big Bang. As we kept going, we would need to get all the way to the 50-yard line before we saw an entire universe full of galaxies. They continued to form across all of those years. And our solar system didn't come along until we were all the way on the other 33, 34-yard line, somewhere right in there. It took a long time for the solar system to kind of carve out its path going around our sun. And ocean life on Earth, after Earth finally formed, didn't happen until about the 25-yard line. We're on the other side now of the football field, to the right, closer to today. All right, and as we keep on moving, we are almost at the goal line before all of these things happened. So you can see what I have listed there when dinosaurs came into the scene, and then when they went extinct from a massive global event. Oh, we got hit by a pretty big chunk of rock flying through space. It took out the dinos. And humans really, they didn't come on the line until inside the 1 yard line. And civilization as we know it today, so civilization, like buildings, plumbing, etc. We can think like Rome. That didn't happen until you were within the width of a piece of paper at the goal line right here. So if you stand up a piece of paper on the goal line on the football field, and you're just looking at the thickness of a sheet of paper, that's only how long civilizations have been around. Pretty crazy about when we are in our journey. And so here it is, kind of all laid out. We've got it all together there, and I mean, we have barely been here. We've been around for just a moment compared to the amount of time the universe has been here. On Schoology, I've shared a video that shows just Earth on a football field. I happened to be searching on YouTube and I came across it. It's not the entire universe like we just did here, but imagine if you took what is mine on here, like between number 5 and 6, somewhere right in there, and took like 5 through 10 and those events and stretched it out across the football field. That's what they show. It's really interesting. So if you want to take a look at that, it really flushes out um, life here on Earth as far as humans are concerned. And it's a great video. So if you get a chance, take a look. And another one that shows this thing that we just did on a football field, they spread it out into a calendar year. So they go January to December. Another way to sort of organize it in your mind. Both of them are excellent videos. If you're curious, you can take a look at those. They are linked on Schoology. All right, let's talk about star formation. And I'm going to start with just a quick video here. We'll let Bill Curtis do the talking for you.
All you need to make a star is hydrogen, gravity, and time.
Gravity pulls the dust and gas into a giant, swirling vortex.
Gravity brings matter together. And when you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up.
Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center.
That really shows you how violent a process star formation is. These jets are many light years across. Something is literally accelerating material very fast across unimaginable distances.
Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born.
Cycle of stars. Make sure I'm recording here. Okay, good. So like you were just seeing on that past little video, stars are formed in nebula. And nebula are areas of gas and dust and particles, and everything forms together. I picture it like you've got little clumps in your house of dust rolling around, little dust bunnies, and as they roll around more and more, they get bigger and bigger. It's kind of like that. Or like if you have a snowball and you intentionally roll it in the snow to make it bigger to create a snowman. That's sort of what's happening in a nebula. And then you've got two different paths that can happen here. You can either just have an average size star, which is like our sun. Our sun is very much average Joe. Or you can end up with a massive star, and they have two very different life cycles. When they're in this state right here, either one, a massive star or an average sized star. They're just in a balancing act. They have the thermal pressure from the inside of the star pushing out. They have gravity, their own gravity pulling back in on that, and it's a very delicate balance for millions and millions of years. But then eventually the gas tank starts to run out, and once you get to the red giant and or red supergiant phase, this is where the star begins to die. So if we were going to label it here, this is the birth is over here. This area here is life. And then all the rest of this over here is how a star dies. Um, all of it to the right. So let's talk about our sun. What's going to happen to our sun? It will turn into a red giant. And so um, the thermal pressure is going to push out, and it is going to push out enough to where it is going to expand. There's actually very, very nuanced things are happening on the inside of the star here. It collapses in and can no longer hang on. And so those outer layers are shed to the outside, and it like blows up really big. And because of the size that our sun is right now, it will eventually turn into a red giant that will engulf all of the inner planets, including the planet Earth. And then eventually those outer layers just shed off, and we call that a planetary nebula, and you're just left with like a little hot burning core. And then all that little shedding eventually gives way to just that core, and you're left with a white dwarf just hanging out in the universe. Um, let's say now you are a massive star, and instead of a red giant, you turn into a red supergiant. It's the same process. The balancing act gives way, and it gives way to the point where it can completely go supernova and explode. Um, we have actually captured supernova. It's hard to catch. It's funny that all of these things take like, millions and billions of years. And then when it goes supernova, it can have it in a moment, just like a few seconds. And so for humans to catch that ever on film is rare, but you can do a quick Google search or even just get onto YouTube and find some things from NASA about catching supernova. Once it goes supernova, massive stars have a much more exciting death than our sun. They can either turn into a neutron star, which is cool, it's just like shooting jets out into the universe on either side, or it can turn into a black hole. And black holes could be a complete course all on their own. Amazing, amazing things to study in our galaxy. Okay, so again, it's a little bit of a balancing act. This is when stars are living. These two forces determine the stages. We've got that outward thermal pressure. Fusion is happening on the inside, and gravity pulling it is nice and balanced. Star lives for a very long time. And then this is where you would see the types of stars. So this is the Hertzsprung-Russell diagram. And these two people went ahead and mapped all of the different stars based on their temperature and their luminosity, their brightness. And so our sun, we went ahead and said, well, our sun we're going to just call a luminosity of 1, and we're gonna measure up all the other stars in the sky based on our sun. So if it's brighter than our sun, it's this way. If it's dimmer than our sun, it's that way. And notice that the temperature scale here is backward. It's cool. I like showing this one to my students because it hurts their brain. But you can see that most stars are on the main sequence. Most of them are living out their life somewhere in here. And it's only when they begin to die that they move off to the edges of temperature and brightness. So you can see that blue supergiants, red giants, all those things are incredibly bright. They can be seen across the universe. And white dwarfs, although super hot, are not very bright at all and very tiny. Okay, so I have listed on Schoology some other videos that you can take a look at regarding star formation, but I want to talk about misinformation a little bit here today. And like we were talking about at the beginning of this video, we're going to focus on this part of critical thinking as it regards to memory and maybe conflating information into our own memories, and something also called the misinformation effect. Let's start out with some space myths while we're still talking about stars and star formation. So, black holes are not a hole. They are a dead massive star, like we were just looking at in the last image there. They're spherical, like our sun. They behave almost exactly like any other massive object in the universe. So the speed required to escape a gravitational pull of an object, whether it's a planet or a black hole, like it takes us 17,000 miles per hour to get off of our planet. It's known as an escape velocity. So our sun has an escape velocity of about 600 kilometers per second, and a black hole has an escape velocity of 300,000 kilometers per second. So it's much harder to get away from a black hole. And even light is not fast enough to get away from a black hole, which is why it is black. But it is spherical and it is a dead star. It's not a hole. Um, and then the moon. The moon has a dark side. Nope, there's no dark side of the moon, despite what Pink Floyd would say. Our moon is geosynchronous. You can look up that word if you need to. Here, I'll write it down for you. Our moon is geosynchronous, and it means the same side is facing us all of the time. So we never see the other side of the moon, and that is what people are referring to when they say there's a dark side of the moon, because the moon is rotating at exactly the same rate that it's revolving around our planet. So we're only ever seeing the same side. We have sent probes around the other side of the moon, so we do have images and footage of the other side of the moon. It gets light. It has new moons and half moons and waning and waxing, just like our moon does that we see from here. That side of the moon also receives light in the same manner. Another myth is that constellations are the stars in them are close together, and that just makes me think of The Lion King, where they're talking about how like the the sky is just flat and it's just like dots on the ceiling. Um, but stars can be hundreds, thousands, millions of light years away from each other, and it's just our perspective. The Earth is not closer to the sun in the summertime. In fact, we're further from the sun in the summertime here where we live. But seasons are caused from the tilt of the Earth, not the distance from the sun. And you cannot see the Great Wall from space. The ISS astronauts, the International Space Station, they can't really see any man-made structures from space. What they do see, though, are lights, like at nighttime. If there are mainly first world countries are very, very bright, and they can see that from the International Space Station. So on Schoology, I've given you links to a lot of these things that we've been talking about, and I came across this article that was disheartening because actually I believed a lot of the things on this list. There are several. But for example, different tongue parts, there's not a section for bitter, sour, salty, and sweet in umami. What? I it's so crazy how we think that. And so I've got a video for you to take a look at. It's super short. It's like 4 minutes. And they walk through how an entire civilization of people, meaning all of us, have thought that that is indeed true. And so the way that the person walks through that video and how misinformation like that sticks and moves from generation to generation from a piece of research is really fascinating to take a look at, and actually one you might want to show your students. So when you get on onto Schoology. This is a good one for students. Plus, anyway, maybe show them this list because maybe they, like me, maybe they thought some of these things. So take a look at that. And then Elizabeth Loftus did a TED Talk. She's a researcher, not the woman you're looking at here, regarding like eyewitness attempts and or attests. People that were an eyewitness to something, and it's really, really fascinating research about the misinformation effect. And it's when your memory of everyday events or past personal experiences become less accurate. So you find out something else later, or the way somebody talks to you, or the way it's written about in the news, or you see it on TV, or you're talking about it with a group of people, something like that. And post-event information starts to get conflated with what you actually saw. And so I want to show you just a little part of this video here.
We're on location of a movie set in the 1950s, complete with cameras, bossy director, and on-set police for security. We've also invited a group of spectators to watch the film. Pay attention along with them as the crew gets the final shot of the movie. Try to remember what you see.
There we go. Final shot, everyone. Action!
Keep watching. Everything you see is fair game. Okay, that wasn't part of the movie. Did you catch what just happened? I know, it was a lot to take in. But we're going to let you in on a little secret. The actors, director, crew, and police are all in on it. Everyone, in fact, except our spectators. And former Las Vegas Police Sergeant Chris Curtis is here to test your memory. He's going to ask you and our other witnesses 3 questions about what you just saw. Ready?
What color was the car that got hit?
Think back and try to be accurate. Got your answer?
Did you say blue? Good. That's correct. Next question. How fast do you think the car was going when it bumped into the other car?
What do you think? Was the red car going 10, 15, 20, 30, or 40 miles an hour? Got your answer? Did you guess around 20 miles an hour? If so, you agree with 80% of people we showed this video to. Before we reveal if you're correct or not, let's see what our spectators have to say.
How fast would you say the car was going when it smashed into the other car?
I'd say 40.
Between 40 and 50.
I was going about 30 miles an hour.
Definitely 50 miles an hour.
These people think the speed was really high. Is that what you thought? Or did you think it was much lower? It turns out the actual speed was 20 miles an hour. Is that what you guessed? So why were our eyewitnesses so much higher? The thing is, only some of our witnesses guessed high. Others were much closer to the real speed.
How fast do you think the car was going when it bumped into the other car?
Probably about 10, 15 miles per hour.
15 miles per hour.
50 miles an hour?
Yeah.
Okay, how can this guy think it's 50
Between 40 and 50.
and this guy think it's 15?
15 miles per hour.
After all, they both saw the same crash. But if you've been paying attention, you'd know it's not the crash that matters, it's the question. Listen carefully to Sergeant Curtis.
How fast would you say the car was going when it smashed into the other car? How fast do you think the car was going when it bumped the other car?
Did you catch it? He said smashed to some witnesses
Smashed into the other car. Smashed into the other car. Smashed into the other car.
and bumped to others, including you.
When it bumped the other car.
The word smashed actually increased the speed of the red car in our spectators' memory.
So I want to tell you, the actual speed of the accident was 20 miles an hour.
I don't believe that. That's crazy.
Yeah, that would surprise me.
It seemed like it was 30 miles an hour.
You're kidding, right?
That's a big difference.
It's incredible if you think about it.
Okay, so the National Institute of Health puts out a little kind of pamphlet about how to tackle misinformation. A lot of this came out post COVID, and with anti-vaxxers and that sort of thing. And they have what they call their three-pronged approach, and these are the three things that you can read on the screen here. But they go a little bit further with a call to action. This Dr. Wardle is really trying to get just really, if you look at the top here, clinicians, government agencies, community-based organizations, libraries, journalisms, et cetera, and she probably means us teachers. It's a call to action um, to be a little bit more preemptive to stop misinformation. And so I linked this article for you. You can take a closer look at it, but you can see some of the things here that she suggests to help combat misinformation. And I like that it's sort of a call to action to people to have a coordinated approach to really make sure that the right information gets out there. One of my favorite things that's written in here is posting in the same spaces where people are describing confusion, where people are spreading misinformation. They're saying that people like us and people like government agencies and etc., should be also putting out social media campaigns with the right information, and that we should be allocating resources to do that. And I think it's an amazing idea if we're going to have informed citizens. But take a look at that article when you get a chance. It's linked there. It's actually not very long. I've showed you most of it here, but you can maybe use that in your classes as well. And so, lastly, what I was going to say about that is just as a side note, I had started a campaign for teachers to tell their own story through our union, through our teaching union, Local 1211, and I was telling it, tell your story, tag your union, because there's so much misinformation about what goes on and what doesn't go on inside the walls of our schools. And so if you haven't already, maybe follow on social media our union. And if you do get on social media with things you do in your class, tag us. And actually, I'm the one that runs our social, so I would be the one resharing it. So you can tell your own story, and that can be like our little call to action here in this class, is to try to get our own factual information out into the world about teachers. So let's go ahead and take a look at, so for week 2, how stars are formed, when we are, where we are in history. I wanted to show you what's here. So I do have a must complete section. I want you to take a look at the TED Talk by Elizabeth Loftus and her misinformation effect. And then I've got all of these other things down here for you to take a look at. Quite a few. Most of them are pretty short. There's a whole list of space myths here. Here's that giant list I thought maybe you should show your students. This is that little one-pager from the National Institute of Health about how we can tackle misinformation. As teachers, I strongly believe we need to be telling our own story. Stop letting other people tell our story for us. And then the space science kind of stuff is down here if you're interested in looking at that. Let's take a look at what the actual assignment is for this week. It's very much like it was last week. You have an option. Make sure that you're commenting on other people's. Let me know what option you started with. And so basically option 1 is just to discuss your specific ideas about misinformation or myths in your course and attach some sort of lesson plan or student assignment, something that you're thinking about. Of course, it can just be in draft form if it's an initial thought. And then option 2, again, is to watch a movie from this list. Of course, you can pick your own movie. You could pick a TV show or something that's relevant to your course as well. This is space science class, so of course I included these space science things here. But you can feel free to, swap that out with something different. And I want you to frame your thinking around time. for this week. Last week we were looking at size and scale. This week I want us to be thinking about when are we? Maybe how fast can we travel? How far away are things? What technologies, et cetera, et cetera. And so, again, I think it's even better to watch with someone, child, really good idea. And go ahead and use your critical thinking skills to look for misinformation or the misinformation effect, or just flat out myths is good too to get our own thinking a little bit sharper. So you have a lot of freedom here to kind of take these in whatever direction you feel. If you could please make sure you post before the next week so that we can have some good back and forth with discussions. If you're late to the game, make sure that you're commenting. If you were early to the game, make sure you go back in and do some commenting on other people's posts. And I will see you for another asynchronous week, week 3. We're going to be talking about exoplanets and conspiracy theories.